I'm going to discuss a problem that often comes up in implicit research, but can come up in any research. And that's if you select a subset, say, of participants, or a subset of items, and then you presume that you can treat that subset of items as having the property you selected on. So, for example, you might select items that a person said low confidence for, out of a larger set of items in which they had a range of confidence. So you take that set which they've said low confidence, and then you say, we've measured this confidence accurately, it has low confidence. And that seems an intuitive thing to conclude, but there's a problem called regression to the mean, which makes it problematic. And so what I'd like to do is discuss that problem. I'll present a solution that we used in a paper by Lena Skora for subliminal perception. Razvan will be talking about the use of the same solution later in implicit learning paradigm. And Matteo will be talking about another solution later on. So what is the problem? Let's say the subject says, I'll just make it simple and say there's two confidence ratings, and they say some trials are going to say whether they purely guessed the answer or they had some degree of confidence. Now, whenever we measure anything, there's always some error in measurement, let's presume. So sometimes when the subject says, is genuinely feeling that they're guessing, they'll say they have a bit of confidence. And sometimes when they have a little bit of confidence, they say they're guessing. That's the error in measurement. I mean, how do we know whether that happens or not? So let's take a particular case, and I'll work through the numbers. And then from the numbers, you'll see a solution, basically. So let's say 70% of trials are genuinely conscious. Say, in the sense we're using subjective measures, that they give an answer and they feel some confidence in their answer. If it's subliminal perception, they say, on a forced choice test, they say, it was this word that was presented, and they have some confidence in it. Or in implicit learning, they choose an item in an artificial grammar learning task, and they feel they know the structural knowledge that was behind it. So let's say it's conscious on 70% of trials and 30% it was unconscious. But there's a error of 10% that arises in both cases. So what I'll do is assume that the error is 10% in both cases. And what I mean by that 10% is in the 7% of trials that are conscious, 7% will be labelled as guess. That's 10% of that. Okay. And in the 30% that are unconscious, 3% of those will be called sure. In other words, will be labelled incorrectly by the subject. So this is how it pans out then. 70% are actually unconscious. But because of the 10% error, 7% are called, 70% are actually conscious, 7% are called unconscious, 63% are called conscious. And of those that are actually unconscious, 30%, because of the 10% error, 3% of those will be measured as conscious. So this is about the simplest model you could have of the error in measurement that can come about when a subject is giving a subjective measure. Now you see the problem that arises here is what we measure as unconscious is this 7% and this 27%. So we measure 34% of trials as unconscious. But only 30% are actually unconscious. So there's an error in measurement. So we think there are more unconscious trials than there really are. So that's the problem that can confront implicit cognition researchers. So that proportion, the 30% that is actually unconscious, is moved towards, in our measurement, to a higher number, because there's more conscious trials. So it moves towards the number which there are more of. So this is regression to the mean. If you plot the true proportion of unconscious trials against the measured proportion, the line doesn't go from 0 to 1. It doesn't have a slope of 1, in other words. The line is tilted. So when the true proportion of unconscious trials is actually 1, you're measuring some conscious trials. And when the true proportion of unconscious trials is 0, you're measuring some unconscious trials. I mean, this is the case that the skeptics of implicit learning get excited about, because they'll say, well, it may be that there are no unconscious trials at all, but you'll still measure some. And because it's based on conscious knowledge, you're going to get some performance above chance. So how do you know, then, that when you're measuring unconscious trials, they're not really conscious trials? Two conclusions follow from this simple model: that if there are more conscious than unconscious trials, the measured proportion of unconscious trials will be too high. That's this case here. So for this part of the graph, there are more conscious than unconscious trials, so you're going to measure too many unconscious trials. And more problematically, unless there are no conscious trials, there'll always be contamination of your measured unconscious trials. Because of measurement error, there'll always be contamination. So the conclusion that skeptics, and especially David Shanks for this particular argument, can be tempted to come to is it's useless to select trials measured as unconscious. You should never do post hoc trial selection because of the regression to the mean problem. So, is that right? But I'd like to argue that conclusion is false. And there's a genuine problem there, but the problem can be dealt with, and we need to think about the problem. We can't just sweep it under the carpet, but there are ways of dealing with it. So what we can do is take these... take this sort of simple model where there's a sort of an X% error that will apply to both conscious and unconscious. And then you can see that the measured proportion of unconscious trials depends on that error, in this case 10%, times the number that are actually unconscious. That's the 7% there. Plus the degree to which you're measuring correctly, 1 minus there, in other words, times the number that are actually unconscious. And that's what I've written down here. So I've just written down here abstractly the concrete case I took you through before, so it's not tied to 70% or 10% or anything in particular. Now you can just then rearrange that equation to say, get a formula for the proportion of observed unconscious trials, how that depends on error and the true unconscious trials. And you can get a formula for the amount of conscious contamination. That's just rearranging the formula that I sent you before. So the amount of conscious contamination in the previous example, 7% was the amount by which was the percent contributed to our measured unconscious trials by actual conscious trials. That 7% are actually conscious. So that's the contamination, that's 7, out of the 34% that we measured in total. So there's a 21% contamination, in other words, for that previous example. In other words, of all the trials we measured as unconscious, 21% are actually conscious. So given this model, we can put a percentage on it. Now, the trouble is, obviously the amount of contamination depends on our error in measurement. I gave you the example of 10%, but we don't know what that error is. Okay? That's an unknown. But limits can be placed on it. We can know what the maximum value is. And this can be very useful, because if we can say what the maximum contamination is and we can control for that, then we've controlled for the worst case scenario. And if we control for the worst case scenario and we still get evidence for unconscious knowledge, we can be happy. So let's say subjects say guess 90% of the time. The maximum error you could have is 10%. Because that would occur if all of the 100% of the trials were unconscious and you had a 10% error. Now, you might think you get maximum contamination when the error is as big as possible, but that's not so. That should be when true unconscious is 100%. Because when you get the maximum error, we assume the maximum error when 100% of the trials are unconscious. Okay. And then 10% of those are said to be conscious. That's our maximum error. But that means there's no contamination in the 90% that the subjects were saying yes to. Zero contamination. On the other hand, if there was 0% error, obviously there's no contamination either. So the maximum amount of contamination happens in the middle of the range. Not 0% error, not your maximum error, but in between. So for Lena's experiment in subliminal perception, Ryan Scott, who was a primary supervisor, just put this equation in an Excel spreadsheet to work out what would be the maximum level of conscious contamination given an observed rate of people saying guess 90% of the time. And indeed, it's bang in the middle. It's when the error is 5%. But then the conscious contamination in that case is only 0.3%. And that's the maximum amount of contamination that could arise from regression to the mean. If people said guess 80% of the time, this is in a registered report, so we laid out our limits in advance of seeing the data just to see what worst case scenarios were. If people said guess 80% of the time, the maximum contamination would occur with 11% error, which would be a 1.6% contamination. Now, how would that contribute to performance? Let's say performance is D prime. We can have an estimate of what the D prime is on conscious trials. We do have that estimate. In this particular case, we ran an experiment where people saw things consciously. Razvan could take the cases where people said, with the structural knowledge attributions, that the structural knowledge was conscious. So we know how well people do on the conscious trials. We have an estimate of it anyway. And then we can say, well, if 1.6% of the trials were contaminated like that and the rest they performed at chance, what's the maximum performance people could achieve due to conscious contamination? In this case, 0.02 D prime units, we can ignore it. We don't have to worry about regression to the mean. But we can do something more general. Let's say it's something you wouldn't necessarily want to ignore. It's D prime of 0.3, or percentage correct of 1% or 2% or something. Well, we can deal with that, okay? You can then set up a null model. You can say, on the model that there is no implicit knowledge, we don't have a point null hypothesis anymore. The people say perform at 50% chance, or D prime of 0. We can have an interval null hypothesis that says people perform anywhere from 0 up to that maximum value we've identified. So this is this rectangle here. That's the model of H0 now. It's saying, even if there is no unconscious knowledge, people's performance could be anything up to, say 0 and a D prime of 0.3, if that's the value we've estimated as the maximum. And then you model your H1 here, however you would normally model it. This is for a base factor. And then with the base factor, you compare, you get the evidence for your H1 versus your H0. So assuming a constant error percentage, regression to the mean is not an insoluble problem for implicit learning and implicit cognition studies generally. The problem can have defined limits. I mean, in some cases, those limits might be too high, and you have to forget about it, but it's worth looking at this to see. Future problems. I assumed the error was constant, it was symmetrical. It was an equal 10% for true conscious and true unconscious trials. Can we relax that assumption? Notice some people like Delaney might be, a skeptic might say, whenever people say something was unconscious, that's always an error. And I don't need to presume that's the same percentage error as for when people say it's conscious. In other words, when people say something's unconscious, when they say it's guess, that's always an error. When people say they have some confidence, that's never an error. A skeptic can say that, but that's unfalsifiable and therefore uninteresting. Now, a month or so back, I looked at this paper by Rothkirch, David Shanks, and Guido Hesselmann. They also looked at the regression to the mean problem, and they argued that in some cases they used an equation that follows from regression theory to say regression to the mean had been a huge problem before in a continuous dependent variable. I was dealing with categorical case, sure or not sure. This is a continuous case. But when I took their formula, well, one thing about the formula is symmetric, like the one I gave. So in other words, they're assuming symmetry as well. So that sort of follows naturally from the regression to the mean situation. But you could take the formula they use, and if you apply it to individual scores and rearrange it a bit, so this isn't what they did, I'm just using the same formula, we can correct each individual score according to their formula, and we shrink the values. We shrink them towards the mean. That's a correction for regression to the mean. We shrink the values according to the error in measurement. Now you post-hoc select after that. That's my suggestion. You can do it with a continuous case. Simone Malik is doing some simulations now to see how far we can push that, what are the limits of doing that, and it still gets accurate results. So this is a now solution for continuous measure like D prime, and the solution I went through is sort of a categorical guess. Sure. So in sum, regression to the mean is something to genuinely think about, but is not at all a reason for not post-hoc selecting trials or subjects. And Mateo, as I say, will be talking about yet another solution that can apply. It's a completely different sort of solution, so you can pick your solution as best fits the data that you're dealing with. All right, thank you.
This might be a totally stupid one, and I'm not saying I completely understood everything you said, but do you think this is something that is generalizable across different types of responses? Like you were talking about conscious and unconscious evaluation of your answers, but like for example in our talk you had to make decisions in the two alternative first choice task, you have to select one of the strings that was grammatical or morphology. And you did that with certain degree of certainty.
Yeah.
Do you think that would be...
It would apply then if you then selected certain subjects out of the larger pool of subjects, said they're implicit, or you selected certain item or item types.
Like if I wanted to select those participants who showed evidence of learning by showing
yeah. Yes, exactly. So this is regression to the mean would show up there. So in that case, you're not selecting for being unconscious. You're selecting it for there being learning. And you can get regression to the mean in that case as well. That's exactly right. Yes.
Many other situations.
Yeah, exactly. So any situation where you select on a measure, a subset, and then you take that subset and you say, and you think you've measured that property in an unbiased way. In fact, you haven't, because you're selecting out on a certain measure that you measured on, and you've assumed your measure had no error when you're doing that. Yeah.
So I was wondering, because here the way this is done, you you are assuming the error in general for the entire sample for all the trials, right? Would there be a way to find out for each participant what do they actually mean with guess, so that we can actually get an error measured for each participant?
So there is so I think there's two things there. One is, could you do this on a participant by participant basis, which is more or less the sort of thing that that's what you do. Yeah. So for each participant, you could have you could do this process individually for that participant. Yes, that might in fact be a better way of doing it, given, as you say, each participant probably has. What this doesn't take into account is individual differences, variability over subjects in that percentage error. And you're right. So one should take into account individual variability in the percentage error across participants. Yes, that's right. And then the other thing was, what do participants mean by guess? I mean, this doesn't really address that, but I've always thought you shouldn't just label something guess or low confidence and call that implicit. No, you shouldn't do that. And then think that when you take those guess scores, people thought they knew nothing at all and sincerely and earnestly thought that, no, you can't assume that. So you need to define, and this is part of a larger thing, point I think psychologists are very bad at, which is caring about the meaning of the scale points and the units in which they're measuring. As soon as psychologists get something, they often try and standardize all the measures and forget about the units, and I think that's a seriously bad thing to do. And this illustrates why you should care about your measures and make sure that when you label the scale point of guess, you've carefully explained what that means to subjects.
Yeah. And I mean about that, I think also another way would be to just like establish a threshold for what guess is with different difficulties on the type 1 or something like that, so that you actually can predict what an actual.
You mean what type 1 D prime corresponds to a guess, which is sort of that sort of thing that you do. But that doesn't mean that the meaning of guess is different for different subjects. It might just mean that subjects sincerely think they know nothing in those cases, but they have different type 1 D primes. And that would be expected as well.
And another thing, so you mentioned that if, for example, you have a D prime of 0.2 as an error, then you can just ignore it. Or
0.02 was the way it turned out. Yeah, 0.2 I wouldn't ignore, 0.02 I would, yeah.
I don't know, like where do we set the threshold with that? Like
if you have any doubt at all, if you put in 0.02, if you have an interval null hypothesis going from 0 to 0.02, you'll get basically the same base factors as if you had a point null hypothesis of 0. So one, unless you ran 10 million subjects, but for sort of, even 100 subjects or whatever, it's not going to make a difference. So one thing you could do is just always put in this correction. Mm-hmm. Then you don't have to make that judgment. You don't have to have that feel for how that would work. And then you get the same number as if you didn't correct for it, because an interval from 0 to 0.02 is as good as a point.
Yeah. Continue in the break. So thank you very much, Volkan.